Hi students, welcome back to the lecture series on electrodynamics, and in this lecture we will discuss about self-inductance. Actually it is a continuation of our earlier lecture, that is Faraday's law of electromagnetic induction. In the next lecture also we will discuss about induction, that is the topic of next lecture is mutual induction. Okay, the present lecture we will define self-inductance, and also we will consider some important topics related to self-inductance of a solenoid, a long solenoid, then self-inductance of a toroid, and self-inductance of a capacitance. Okay, let us start. And in this lecture we will start with an application of induction called eddy current or Foucault current. Then we will have some basic definitions and or related to self-inductance, and some equations related to self-inductance, that is self-inductance in terms of the flux linkage with the coil, and also self-inductance in terms of the EMF induced when the magnetic flux changes. Then we will derive or define the self-inductance, the basic unit for self-inductance. After that, we have to consider in detail the self-inductance of a long solenoid, that is of much importance in different fields, and we will extend that to a toroid coil, that is self-inductance of a toroid coil of circular cross-section, and in a special manner we will extend that into that of a toroidal coil of a rectangular cross-section. And finally, we will conclude with self-inductance of a co-axial capacitor. And the last class, we observed that when a circuit or a conductor associated with a circuit is allowed to move in an external magnetic field, an EMF induces in the circuit, and that generates a current flowing through the circuit. On the other hand, if we change the magnetic field associated with the circuit, or if we allow to move the magnetic field away from the circuit, that case also, in both of these cases also, an EMF induces, similar to that of the first case, that is a movement of the conductor from a magnetic field. So these three cases produces an EMF in the circuit, usually represented by the universal flux rule related given by E is equal to minus d phi by dt. Now the first example that we have considered earlier is that of the movement of a conductor with a velocity v from a magnetic field B. So as it moves, we observe that a current flows through the conductor in order to oppose the change associated with the change in magnetic field associated with the circuit, and the EMF induced is given by the magnitude E is equal to minus d phi divided by dt. The other two possibilities for the induction is, first one is by keeping the circuit stationary, move the magnetic field, or simply allow the magnetic field to move away from the circuit. In that case also we will have the EMF induced in the circuit. And the third case, both magnetic field and circuits are stationary, but we are gradually changing the intensity of the magnetic field, the strength of the magnetic field. So the three cases generates the induced EMF given by E is equal to minus d phi by dt. And from the second and third we concluded that a changing magnetic field induces an electric field. A changing magnetic field induces an electric field, that is of much importance in electromagnetic induction. If a conductor placed somewhere in a changing magnetic field, an EMF induces in the conductor, and if it is if the conductor is not there, we can say that there is a changing electric field in that region associated with the changing magnetic field. Now let us consider a practical example in relation with the moving conductor, that is called eddy current, and sometimes called Foucault current. So an example, we have considered a horseshoe magnet here with north and south poles as shown in the figure. It is the magnetic field is directed from top to bottom, and the conductor in the form of a slab is allowed to move in this direction. It is moving away, or it is moving with the velocity v. So we can see that as the conductor enters the magnetic field. So as the conductor enters the magnetic field associated with that conductor is changing. Actually, there is no circuit associated with this conductor, but this conductor is of a certain size. So the conductor is moving towards the magnetic field means the magnetic field associated with that conductor is changing. So that change tries to oppose by the conductor due to the principle of induction by generating a current within the conductor, and the magnetic field associated with that new current induced inside the conductor tries to oppose the change in magnetic fields. So as it coming towards the magnetic field, the conductor opposes or produces an opposite magnetic field in order to oppose that change. So a circular current generates inside the conductor such that the magnetic field produced is opposite to the direction of the magnetic field. And as the conductor moves away from the magnetic field, the reverse thing happens. That is, at that time what happens is the magnetic field tends to decrease. So in such situation, the conductor produces circular currents within the conductor in order to maintain the magnetic field. So the direction of the current is such a way that the magnetic field produced is in the direction of the magnetic field of the external positive magnet. So during entry time, the magnetic field or the eddy or the current produced inside called the eddy current, and that magnetic field is opposite to the external field, whereas while the conductor is moving away, the current produces a magnetic field in the direction of the external magnetic field. So this is actually known as the eddy current, with a lot of applications in different industrial and household appliances. So let us examine this in a magnified form. Say at the entry point, what happens is corresponding to this particular point, we can see that the magnetic field is from top to bottom, and the conductor opposes that growth of magnetic field inside the conductor by producing a magnetic field in the opposite direction. That means in the upward direction. So in order to get an upward direction magnetic field, the circular current induced in the conductor will be in the counterclockwise direction, as shown by the arrow mark, the counterclockwise direction. So that generates a magnetic field in the upward direction, or based on the Lenz's principle, the growth of the current in the circuit is opposed. And at the time of exit, that is corresponding to this region, the conductor is trying to move away from the magnetic field. The current produced inside is in the same direction as that of the external magnetic field, so that the direction of the current will be in the counterclockwise direction, in the clockwise direction, like this, in the clockwise direction. So in the clockwise means the magnetic field is produced by that current also in the downward direction, that is shown in the magnified form, that is corresponding to this region. The current is in this direction, and entry point as the growth region, the magnetic field growth region, the current is in the counterclockwise direction. So this type of current induced inside a conductor, or the magnetic field associated with a conductor changes, and EMF induces inside the bulk region of the conductor, and that produces circular currents inside the conductor due to the resistance of the conductor that generates heat energy, or it is a method for converting electrical energy into heat energy that is used in different applications also. Now let us come to the definition of self-inductance. The basic definition: whenever a current flowing through a coil increases, the magnetic field associated with it increases, which in turn induces an EMF in the coil. in order to oppose the growth of the current in the coil. So it is quite clear. That is, we have a coil and a current is allowed to flow through the coil, and during the process of increasing the current through the coil, an EMF induces such that it tries to resist the growth of current. So we know that when a current flows through the coil, it generates a magnetic field, and the magnetic field actually is associated with that coil itself. So the magnetic field associated with the coil is changing due to the current flowing through the same circuit or same conductor. And we know that by the principle of electromagnetic induction, whenever the magnetic field associated with the coil changes, an EMF induces in the circuit in order to oppose that. So in the earlier example, we have considered external magnetic field for the process, but in the present situation, what we are doing is we are allowing a current to flow through the conductor, and that current itself generates or increases the magnetic field associated with the conductor. So whatever it may be the source, that may be from externally or due to the intrinsic current or the current flowing through the circuit. The thing is, the magnetic field is changing. So that change in magnetic field, increasing magnetic field, is protected by the coil by producing an EMF or a current in the opposite direction, or it generates a magnetic field in the opposite direction, or it allows a current to flow in opposite direction to that of the externally increasing current. This process of resisting the making of a current or increase of a current in a circuit is called, the self-inductance of the coil. So here we have considered the direction of the current like this. If from positive is here, negative is here, and the current is moving like this. Current is moving in the counterclockwise direction, and we know that it will produce a magnetic field somewhat like this, magnetic field in this direction. Okay, so in the counterclockwise direction, so this side becomes north and this south. So we can see that due to self-inductance process, an opposite current generates, actual current is this one, but the opposite current, the induced EMF produces a current in this direction, and that produces a magnetic field in an opposite direction in order to resist or decrease the making or the increasing of the current through the circuit. So this is called basic property of the coil, and the same thing happens when the current through the coil decreases also. So during the switching off process, during that process, we can see that the current suddenly decreases. That means that the magnetic field associated with that coil is trying to decrease. That also is not allowed as far as the basic property of the coil is concerned. So it tries to regain the current or make the current by allowing the conductor to increase the current in that direction by making use of an induced EMF. So during the switching off process, an EMF induced will be in the same direction as that, or the current induced will be in the same direction as that of the external current actually flowing. In both cases, we will get the same principle, self-induction principle, and we will represent that in terms of the flux linkage associated with the coil. So similarly, whenever a current flowing through the coil decreases, the magnetic field associated with it reduces, which in turn induces an EMF in the coil in order to oppose the decay, of current in the coil. So in general, we can say that whenever a current flowing through a coil changes, whether it increases or decreases, an EMF induces in the coil in order to oppose the change in current. This property is called the self-inductance of the coil. And it is also called a back EMF. Usually it is called back EMF since it is in such a direction as to oppose the change in current that I have already explained clearly. It always tries to oppose the change happening in the coil. So it is called back EMF. Now the self-inductance is also known as electrical inertia or electromagnetic inertia. Electrical inertia or electromagnetic inertia. The term comes from the property of a material. We know that for a material there is a property called inertia. That is, a body at rest, it is difficult to start in motion. Then when it is moving with a constant velocity, it is difficult to stop the body. This property is called, the intrinsic property is called the inertia. So this inductance is also similar to that of the inertia, mechanical property. So it is called electrical inertia or electromagnetic inertia. So due to the property of inertia, it is difficult to set a heavy body into motion. Also, it is equally difficult to stop a moving body. That is for a mass moving body or a body at stationary situation. Similarly, in a coil of large self-inductance, it is difficult to establish a current. Through it. Also, it is difficult to stop the current flowing through the coil. Therefore, the self-inductance is also called electrical inertia or electromagnetic inertia. So this is another name given to the self-inductance. Now let us define or find out some expressions for the self-inductance. We are going to derive two expressions. One in terms of the flux linkage associated with the coil and the other in terms of the EMF induced in the coil. So two simple expressions, one in terms of the flux linkage phi and the other in terms of the EMF induced E. Okay. So for this coil, we can see that the flux passing through is given by phi proportional to I. That is, as the magnitude of phi increases, the flux associated with that coil also increases. So phi proportional to I. Now that is for a single turn. Now let N be the number of turns on a coil through which a current I is flowing. Now we are simply changing the coil into a coil of N turns. So in that case, we can see that the flux linkage is N phi. That is for a single turn phi. So here we have N turns. So N phi is the total flux. And the total flux is proportional to I, and the proportionality constant is represented as L. The proportionality constant is L, so that N phi is equal to Li, or we'll get the relation that is L is equal to N phi by I. That is the basic equation for self-inductance of the coil. L is equal to N phi by I, or simply phi by I. That is a flux divided by flux linked to the coil divided by the current flowing to the coil. Now, in order to get the expression in terms of the induced EMF, let us start with Faraday's law of electromagnetic induction. That is the flux rule. Flux relation is equal to minus d phi by dt. And for this example, we have considered a coil with N turns, so that the total flux is N phi. N phi is the total flux. And in this expression for the induced EMF, we are substituting for phi as N phi, because we are considering the example of N coils. So E is equal to minus dN phi by dt. And now we know that N phi is equal to Li. As our earlier expression, we substituted N phi is equal to Li. When putting that value here, we'll get the expression for E as E is equal to L di by dt. E is equal to L di by dt. So we get phi by I or N phi by I as one equation, and the other one, induced EMF E is given by minus L di by dt. From this relation also we are able to find the self-inductance of the coil. The next thing is we are defining the self-inductance, how to measure the self-inductance. Now we will consider the coefficient of self-inductance, or what is L. That is what we are going to discuss here. Based on these two equations, we will explain the coefficient of self-inductance and also the unit used for self-inductance. So self-inductance is measured in terms of coefficient of self-inductance. And as our first relation, we have L is equal to N phi by I or phi by I. And we are letting the current flowing through the circuit to 1 ampere. The current flowing through the circuit is taken as 1 ampere. So that this expression changes to L is equal to N phi. L is equal to N phi, that is the total flux passing through, or the inductance is equal to the total flux passing. So the coefficient of self-inductance L of a coil is defined as numerically equal to the flux linkage produced when unit current passes through the coil. That is, L of a coil is defined numerically equal to the flux linkage produced when unit current passes through the coil. When unit current passes through the coil, the flux produced is called the self-inductance, coefficient of self-inductance. Now, this self-inductance may also be defined in terms of the other equation, that is the second equation that we have derived, that is the EMF induced is equal to minus L di by dt. Here we are letting di by dt to 1 ampere per second, 1 ampere per second. That is, the current through the coil is changing at the rate of 1 ampere per second, and in that case L becomes the induced EMF. The inductance becomes the induced EMF. So the coefficient of self-inductance L is numerically equal to the induced EMF when the rate of change of current is unity. So the rate of current, change of current flowing through the circuit is unity. That is 1 ampere per second current change is there. In that case, the EMF induced is called the coefficient of self-inductance as according to the second relation. Okay. Now the unit of self-inductance, see, we know that it is usually represented by Henry, or for small values we will consider millihenry or microhenry, etc. So we can derive or define this Henry based on these two equations again. The first equation we have L is equal to phi by I. And in the earlier slide we observed that when I is equal to 1 ampere, L is equal to N phi. And again we are allowing or letting this N phi, the value of N phi as 1 Weber. That is, if the value of N phi is equal to 1 Weber, then L is equal to 1 Henry. L is equal to 1 Henry. That is, when the coil is said to have, therefore the coil is said to have a self-inductance of 1 Henry if a current of 1 ampere flowing through it produces a flux linkage of 1 Weber. That is, when 1 ampere current flowing through the circuit generates a flux of 1 Weber. 1 ampere flowing through the circuit generates a flux of 1 Weber, then the self-inductance of the coil is considered as 1 Henry. That is the definition. This definition can also be defined in terms of the second equation, that is E is equal to minus L di by dt. And as in our previous slide, we have already taken di by dt is equal to 1 ampere per second, and then we get L is equal to E. And right now, suppose the EMF induced is taken as 1 volt. Then again we will get L as 1 Henry. L as 1 Henry, that is, therefore a coil is said to have a self-inductance of 1 Henry when the current changing at the rate of 1 ampere per second in the coil and induces an opposing EMF of 1 volt in it. That is, when a current changing through the coil is 1 ampere per second, the EMF induced is 1 volt. In that case, the self-inductance of the coil is taken as 1 Henry. So these are the two definitions that we are using for defining the unit of self-inductance. Next, we are going to consider the self-inductance of a long solenoid, a solenoid with large number of turns. And the self-inductance, we will get an expression for the self-inductance, and that is of much useful in a good number of applications, in the industrial and scientific applications. Okay, the method is very simple. We are simply using the basic equations in order to find the self-inductance. Now, the considered example is with total n turns. Total number of turns on the coil is capital N, and small n is the number of turns per unit length. Small n is the number of turns per unit length, so that small n is equal to n divided by L. N divided by L is equal to small n. That is, number of turns is equal to total number divided by total length. So The flux density inside is given by, the expression is given by mu 0 Ni. That is the flux density inside based on Ampere's theorem. We know that the flux density inside is equal to mu 0 Ni. And when substitute for small n, it is equal to mu 0 capital N by L into I. Anyway, we are proceeding with this equation. B is equal to mu 0 Ni, that is number per unit length. Now the flux through a single turn of the coil is taken as B dot A, or simply B into A. P into A in this case, because B is the flux density and we are assuming that the magnetic field inside the coil is constant throughout the area of the coil. The B is assumed to be constant, or it is constant throughout the entire area of the coil. Within the coil, it is constant everywhere. So we are simply multiplying B into A to get the total flux through single turn, or the flux associated with a single turn, and it becomes mu 0 Nia. Mu 0 Nia is the flux associated with the single coil, because mu 0 Ni is B. Simply multiplying with the A. So that flux through the entire solenoid, means simply multiply with capital N. Capital N is equal to NL. So simply take this equation and multiply. So phi, total flux phi is equal to mu 0 Nia into NL. Mu 0 Nia into NL. So mu 0 Ni is the expression for B, and A is the area, so that's the flux linkage with one coil. Then multiplying with NL means the total flux associated with the solenoid, or the expression becomes phi is equal to mu 0 N square IAL. So this is the expression for the total flux linked with the coil. Now let us take the basic equation that phi is equal to Li for any coil. Phi here stands for the total flux. Total flux with the coil is simply given by the self-inductance into the current flowing through the coil. Phi is equal to Li. Now equating this Li at the position of phi, substituting that here, we will have the expression for the self-inductance of the coil long solenoid as mu 0 N square Al, mu 0 N square Al, and this is the expression for self-inductance of a long solenoid. So in place, if we have some material inside in the form of a core for the solenoid, then in place of mu 0 we have to substitute mu as the permeability of the medium within. So L is equal to mu 0 N square Al, and if the area of cross section or radius of the coil is given and length is given with the total number or number of turns, then we are able to find the self-inductance of coil by simply substituting in this expression. Now next is an extension of this problem, that is self-inductance of a long solenoid. Now we are extending that to a toroidal coil. So we are simply closing the ends of the long solenoid to get the toroid, so that the magnetic field inside is assumed to be constant. There is no change, it is constant there. Same expression is there, and the area, the magnetic flux density inside the cross section is again constant in this case also. So there is no much change for the expression, only related to the length of the solenoid. Slight modification is there, and let us check what is the modification needed. So the self-inductance in this case, the earlier expression for the long solenoid, we have it is given by L is equal to mu 0 N square Al, and the fact is that self-inductance of a toroid is same as that of a long solenoid, no change, same expression. Now here N is the total number of turns and S is the average radius of the toroid, so that we can make these substitutions. N is equal to NL and L is equal to 2 pi S. L is equal to 2 pi S or 2 pi R, that is the circumference of the average radius of the toroidal coil, that is the total length of the toroid. And in place of the capital N, small n, we have to substitute the total N in terms of total N. So L is equal to mu 0 N square Al changes to mu 0 N square by L square, that is in place of small n square we have capital N square by L square into Al. So it becomes mu 0 n square, capital N square A divided by in place of L. So we cancel this L square and this L from this side. So 1L remains in the denominator. So it is equal to 2 pi s. So mu 0 n square A by 2 pi s. So that the final expression is like this. The self-inductance of the toroidal coil of circular cross-section is given by L is equal to mu 0 n square A by 2 pi s. The same as that of the starting equation is same as that of the long solenoid. Okay, next let us approach this problem in a slightly different manner. That is, let us consider a toroid coil again with a rectangular cross section. So only one difference is here in comparison with the earlier one. There is one difference. Previous case we assumed that the magnetic field around the coil or inside the coil over a cross section is constant, so that the flux linkage is evaluated in terms of B into A. Magnetic field B, flux density B into A will give the flux associated with one coil. Then we multiply with the N coil. That was a procedure already adopted. But for the rectangular cross section, what is the thing is that the magnetic field is not constant, as the radius or the S value, that is the distance from the center to different regions of the rectangular cross section, increases. The value increases, or as we move one point to the other point, inner radius to outer radius of the toroid, we can see that the magnetic field is slightly changing. So instead of simply taking B into A, we have to take B dot ds. That is the only difference. To consider B dot ds in order to get the total flux linkage with the coil. So flux density inside is given by the same expression that we have considered earlier. B is equal to mu 0 ni, or in terms of the total number of turns, mu 0 n by L into I, or mu 0 ni by 2 pi s. Mu 0 ni by 2 pi s is the flux density inside. And the flux through single turn is equal to B into A. For the present case, we have to evaluate it like this: surface integral B dot ds, and this is the figure of the toroid coil. The current is entering and leaving like this through this terminals. The first and last terminals are shown, and here the value of S is taken. S ranges from the inner radius to outer radius, say A and B. So in order to have a clear picture of this rectangular toroid coil, I have redrawn it in a cross-sectional form. Like this. See, this is a cross section of the rectangular toroid, and here is the point S. This is the point S taken, and corresponding to we have the inner radius taken as A and the outer radius taken as B, and associated with the distance S, we are assigning a small strip of area ds, and height is taken as h. So h into ds is the area of the small strip of cross-sectional area, and we are assuming that there is no change for the magnetic field as move in the h direction, that is from bottom to top. There is no change, but as we move from A to B, its value is changing. So we have to find out surface integral B dot ds by integrating from A to B with respect to ds. So ds, we are assuming that h ds is taken, and we will integrate h ds from A to B. There is no change is in the direction of h, so h into ds is the flux link, the flux area associated with that. So bh ds is integrated between A and B. So surface integral B dot ds is equal to surface integral in place of B. I am substituting this expression that is mu 0 ni divided by 2 pi s dot ds. Here mu 0 ni by 2 pi is taken outside, and h also is taken outside, because surface integral means a double integral. Actually, it is from 0 to h and A to B, double integral. So only we are taking A to B integral here, because 0 to h integral, there is no change, so we are taking h outside here. So integral into, so mu 0 ni by 2 pi h into integral A to B 1 by s ds. and 1 by s we know that it is equal to log b by a. So the expression changes to mu 0 nih by 2 pi log b by a, and the total flux through the toroid coil becomes n times b dot ds, and it is substituted as phi. Phi is equal to mu 0 n square ih divided by 2 pi log b by a. So this expression into n. So this is that given by total phi. Now the next step is quite clear. Equate that to Li, so that L is equal to, dividing this expression with the I, so that I cancels out. So the final expression changes to L is equal to mu 0 n square h by 2 pi log b by a, and this will be the expression for the self-inductance of a toroid of rectangular cross section. Okay, now one more example, that is with the case of a coaxial capacitor, or in the form of a coaxial cable, self-inductance of a coaxial cable. Since a capacitor, a long capacitor or a long cable is considered, finally we will arrive at an expression with the self-inductance per unit length of the coaxial cylindrical capacitor or coaxial cable. Here also the procedure is quite the same. Find the total flux linkage associated with the capacitive region or the conductor, and find out the inductance. So the example is like this. The figure is shown here. A section of the coaxial capacitor with inner conductor and outer conductor. We are assuming that current flowing through the inner conductor and outer conductor. Through the inner conductor, let the current be in this direction. Then we can see that through the outer conductor it will be in the opposite direction, so that it becomes a capacitor, behaves as a capacitor. And let I be the current flowing through any of this conductor. I is the current flowing through the conductor, and we can see that the magnetic field inside the capacitor. This shows the cross-sectional figure of the capacitor with the inner radius A and outer radius B, and we are considering any Amperian loop in order to find the magnetic field inside. The Ampere's circuital theorem, integral form of Ampere's circuital theorem is applied to find the magnetic field inside. So we get the expression as B is equal to mu 0 I by 2 pi r, that is closed line integral B dot dl. B dot dl is equal to mu 0 times I. So this is the expression Ampere's circuital theorem, and for this closed Amperian path it is equal to mu 0 B into, here B is constant, B into 2 pi r is equal to mu 0 I. So B is equal to mu 0 I divided by 2 pi r. So that is this expression, mu 0 I by 2 pi r. So the flux associated with within the capacitor, flux associated inside the capacitor, phi is given by surface integral B dot ds, where we are dealing with the surface inside the cable or inside the capacitor, that is the entire region, and we have the circular magnetic field B inside, and that changes from A to B. The magnetic field inside the capacitor changes from A to B. So we want to find the total using this expression. Phi is given by surface integral A to B 0 to L mu 0 I by 2 pi r dr into TL. So mu 0 I by 2 pi r is equal to B dot ds we are doing. Phi is equal to B dot ds. Now ds in this case is given by dr into dl, because we are taking integration over the radius, that is this flux is changing from A to B, and also it extends up to L, length of the capacitor or cable. So A to B dr and 0 to L dl. A to B dr, integral A to B dr and integral 0 to L dl. So 0 to L dl is simply L, total length, and the other one A to B dr by r, the constant mu 0 IL by 2 pi is taken outside, so integral A to B dr is there, dr by r is there, and that will give log B by A as in the previous example. integral a to b dr by r is remaining, and substituting the limits you will get it as log b by a, and this is the total flux linkage or linked with the coaxial capacitor, and substituting for the total phi as in terms of the inductance, self-inductance Li, and we will get this expression, or cancelling this I from this expression, it will be given by L with the suffix I. Li is given by mu 0 L by 2 pi log B by A, where the suffix is for the total inductance for a length L of the capacitor or the cable. Now assuming that we are only taking 1 meter length of the cable, so simply divide this expression with the L, or simply cancel this L. So the final expression, inductance per unit length is given by L is equal to mu 0 by 2 pi log B by A, and this will be the final expression for the self-inductance of a coaxial capacitor or a cylindrical capacitor, coaxial cable or a cylindrical capacitor. Okay, so we have discussed about the basic principles of induction, self-inductance. The expression for self-inductance in terms of, we have already derived two equations. The first equation is in terms of the total flux linked with the coil, that is L is related to the total flux linkage I. Then another expression is derived in terms of the EMF induced in the coil, that is a relation connecting the induced EMF and the flux linkage. Then the coefficient of self-inductance and the unit of self-inductance, Henry, is defined. Then we have a practical example. Consider different practical examples such as a long solenoid, self-inductance of a long solenoid. Then we extend that into a toroidal coil. Then again it is extended in a special way to a rectangular, a toroidal coil with a rectangular cross section. And finally we have considered the self-inductance of a coaxial capacitor or a coaxial cable. Okay, that is all for this lecture. Thank you very much for watching this video.